the image size was decreased. There is no magnification here. It's just a simple, really very clear. It just shows that for concave lens, tugomba kubimenya. Always we must know, naho turi hose tukabona ko igihe cyose image kamivuge mu kinyarwanda, niba dufite concave lens cyangwa se diverging lens, iki gihe bivuze iki? Bivuze ko diverging lens buri gihe igomba kugira image iri virtual. Virtual image ni image iba. Dear ladies and gentlemen, how are you? Today's session we continue by discussing about it's about a new lesson today about the thin lenses. In this session for today we will discuss about thin lenses. We have so many parts to discuss about in order to have some more information related to this topic. The part 1, as we see, we have 3 parts. Part 1 we will discuss about, we will introduce the thin lenses. What is the thin lenses? What can be the types of thin lenses? In part B we will try to solve, we will try to make together solved questions or problems related to thin lenses. Part 3 it's about unsolved questions. You will be able to try yourselves where you are located, everyone, because we are in different location. So you will try to do yourself or yourselves by using a notebook, a paper, a pen, whatever instrument you can use. The necessary is that you can make it seriously. This part is very essential, is very important. By starting on the first part 1, it's about introduction to thin lenses. When we say thin lenses in the physics or in our daily life are used to form image. Image are formed in 2 ways. The first way is that you can use mirrors. Mirrors can be used to form image by reflection of light. But for thin lenses, light is reflected. Reflection of light. When we say reflection of light, refraction of light, it is a phenomenon occurs in our physics where light rays, when hit the medium, the second medium can change direction. For instance, there is a light ray from air. When air is the first medium, when light hit water medium, the direction of light will change. That's what we call refraction. Whereas reflection, it is a phenomenon occurs where a light can reflect in the same medium. For instance, when you say the mirrors, the plain mirrors we use at home to see our image, light hit on that mirror, then reflect. We have only the same medium. Whereas for refraction of light, we have two media. When there are many, we say media. So let's come back on what you call thin lenses. Thin lenses are in 2 types. We have converging lenses and we have diverging lenses. Converging lenses and diverging lenses. So by now let's start about converging lenses. When you say converging lens, this is a converging lens. The structure and how light rays are refracted they are refracted in the second medium toward focal point. This is a focal point. Whereas for this reflection in the diverging lens, it's not the case. For these diverging lenses, refraction is bending, but the imaginary rays are in the same side as the light source. Let's try to see by definition and so on. So by definition, converging lenses are also known as convex lenses, which are thicker at centers than at the edges. They are thicker at centers than edges. These are converging or convex lenses. It converges parallel to single point called the focal point. These are parallels that converges to focal point. To converge means bending of rays, so that rays can meet at this point, which is known as focal point. Rays are refracted by converging at one point. So the image formed by converging lens should be real or virtual. In one case, they can be virtual, in another case can be real, depending on the object's position relative to the focal point. Always for focal length, the focal length of converging lens or convex lens always is positive. Whereas the equation 1 over f, this equation 1 over f equals to 1 over v plus 1 over u, where f is the focal length. When you say focal length, it is the distance from the focal point to the position of lens. This is what we call focal length. V, it is image distance. U, it is the object distance. We know all of these ones. For diverging lens, it is a lens which is known as the concave lens, which is thinner at centers than at edges. They are thinner at centers than their edges. So also the image formed by these diverging lens or concave lenses are always virtual, upright and reduced image. The image formed by diverging lenses always is the virtual image, which is upright or erect, and always diminished or reduced image. So the focal length of this diverging lens always are negative. So the equation is the same, but the equation is the same as that of convex lens, but the difference is about the sign used. The sign is a key point here. Note, the sign conversion for object distance u, image distance v, and focal length are crucial for using the lens equation. What do sign conversion means in thin lenses equation? When we have focal length which is positive, when the focal length is positive, what does it mean? When the focal length is positive, it means that the lens used to form image is the convex or converging lens. Whereas when the focal length is negative, means it is diverging lens or concave lens. Concave lens always have negative focal length, whereas convex or converging lens they always have positive focal length. That's about focal length. When image distance is negative, image distance will be negative. It means that the image formed is virtual image. When image distance is negative, it means it is a virtual image. What is a virtual image? A virtual image, it is the image formed in the same direction as object, which is erect, not inverted. Whereas the real image, it is the image which is formed in the opposite side as a source of rays, which is always inverted. That's what we call real image. Real image always are inverted. So when magnification is negative, means that the image is also inverted. When magnification is positive, it means also the image is upright, means a virtual image. Now let's continue on another point. Let's look about the focal point of combined lenses. It is possible in optic or in thin lenses can be combined. It's a case. It may be. Sometime image can be lenses can be combined, lenses of different focal length. In case there is combination of lenses, the reason why we are going to see what is the focal length, because focal length determines the power of lenses. So in combining lenses, there is two cases. Case number one, lenses they are combined so that they are in contact. Maybe also the lenses can be two, like in a microscope, so that there is a distance separating the two lenses. The reason why we are going to see what can be the power, what can be the focal length in case there is combination. So a lens is in contact when two thin lenses of focal length f1 and f2 are placed in contact. The focal length of combination, which is capital F, sometime is given as this formula. When you have two focal lengths, it means you have two lenses. They combine the focal length. Focal length as a result from combination will be equals to the inverse of focal length number 1 plus the inverse of focal length number 2. Means the power equals to power 1 plus power 2. This is the ability of these lenses. In case there is separation, lenses separated by distance. When two thin lenses are separated by distance d, the power is given by 1 over f, which is equal to 1 over f1 plus 1 over f2, but minus d, the distance separating the two, over the product of two focal lengths. This is the power of focal length. This is how we will try to calculate the focal length in case there is combination of lenses. So in this part 1, let's also talk about magnification of combined lenses. So when you say magnification, what is the magnification? When the magnification is the measure, we can use to see whether the image is magnified or diminished. It is measured by comparing the object size and the image size. When the image is very bigger than or compared to the object, in this case, magnification is high, means there is there is high power of lenses used. So magnification is given by the product of when there is a combination of lens, but firstly magnification equals to the negative side. It is the ratio of image distance over object distance, but this negative sign also is applied. This is magnification. But the total magnification in case there is combination will be equals to magnification number 1 times magnification number 2 times magnification number 3, and so on. It depends how many lenses do you have, so that we can find the magnification as the product of individual lens. M is the magnification, V is image distance we know, and U is the object distance. So let's jump to the next part. The second part is about to try to see by applying all information obtained here from this converging lens, means also diverging lens, also the focal length, even the magnification. Let's apply the result or the information discussed above to see this sample of questions solved. Then after the last part, we will show you unsolved question to help you to test yourselves so that we can get better results. So let's start on the first question. It's about basic calculation. It's very simple. They are not too complicated. It's just very simple. It's just to help you to try. A complex lens has a focal length of 20 centimeter. An object is placed 30 centimeter from a lens. Find the image distance and the magnification. So it's a very simple question. We have focal length, we have object distance, we have this question. 1 over v equals to 1 over f minus 1 over object distance. Then it's the remaining is to replace the given number by a symbol. By calculation, we will see that the image distance equals to 60 centimeter. As you see, it is positive. The image distance is positive because it means that the image is real. Okay, good. The image, if v is positive, it means that the image is real. When v is negative, the image should be virtual image. So magnification, it is the negative sign times the ratio of image distance over object distance. The image is real, inverted and magnified. So the second question, a concave lens has a focal length of negative 15 centimeter. An object is placed 20 centimeter from a lens. Find the image distance and the magnification. This question also is the same as the first one, but here we have concave lens or diverging lens. Focal length always is negative 15 centimeter. Object distance is positive, always 20 centimeter. The equation is the same, but when we substitute or replace the value by its symbol, we will see the image distance is negative. It means that the image is a virtual image. It is a virtual image, so that this negative sign means the image is the same the direction as the object. So magnification, as we see, there is the diminution, also it is diminished. The image is virtual, erect, and diminished. So we can consider all this one. For concave lens, always image distance should be negative, means it is a virtual image and diminished and erect or upright, we can consider this point always. The third question, an object is placed 25 cm from a convex lens and forms a real image twice the size of the object. Find the focal length of the lens. We have here a convex lens where the object distance is 25 centimeters, where magnification is -2. To say it is -2, it means we have a real image. We have real image, which is the reason of this negative sign, because it is for always, as we see, magnification equals to 2, because the real image twice the size of object. Find the focal length. We just apply this formula, then we find the focal length, which is equal to approximately equals to 16.7 centimeters. Question number 4, it's about also the concave or diverging lens. A 5 centimeter tall object means the height of object is placed 40 cm from concave lens. The image formed is 3 cm tall. We have the size of object and we have size of image. Because it is a concave lens, the image should be diminished. We see when you compare 5 and 3, there is a change. Find the total focal length of the lens. So we were given height of object, which is equal to 5 cm, height of image, which is equal to 3 cm. Also the object distance, which is equal to 40 cm. Magnification we know. Also another formula we use for magnification, it is the ratio of size of the image to the size of object. We see there is it is equal to 0.6. There is a reduction because it is less than 1. Using the magnification equation, we can see that the image distance will be equal to -24 centimeters. Then after getting this magnification, also the image distance is very simple to get. Then we will apply this and then find the focal length, which is called -60 centimeters, means for the diverging lens. Let's continue to these are the basic question. By now, let's continue on this question regarding to the image formation and the characteristics. Image formation and the characteristics. So, a convex lens of focal length of 15 centimeters forms a real inverted image 3 times size of object. The image is higher 3 times than object, means there is magnification. Find the object and image distances. It's just to apply the formula related to the magnification, then use a lens formula equation. Then we see that V would be equals to 3U, then would be equals to image distance 60 centimeters. Object distance is 20 centimeters, image distance is 60 centimeters according to the calculation. A concave lens of focal length of -20 centimeters form a virtual erect image half the size of object. Half the size means the image size was decreased. There is no magnification here. It's just a simple, really very clear. It just shows that for concave lens, tugomba kubimenya. Always we must know, naho turi hose tukabona ko igihe cyose image kamivuge mu Kinyarwanda niba dufite concave lens cyangwa se diverging lens. Iki gihe bivuze iki? Bivuze ko diverging lens buri gihe igomba kugira image iri virtual. Virtual image ni image iba iri mu cyerekezo kimwe cyangwa se muri side imwe na object, kandi ibireba hejuru, ntabwo iba icuramye. Kandi image yabaye formed iba ari nto ugereranyije n'iki? Na object twagize gute? Twari dufite. Image iba ntoya ikaba mu cyerekezo kimwe naho object iherereye, iyo tukayita iki? Virtual image, image itagaragara. Ikindi, image distance iba negative, iba ifite sign ya negative. Mu gihe kuri convex lens cyangwa se converging lens, image distance igomba kuba ari positive cyangwa se negative, hose birashoboka, kubera ko dushobora kubona real image cyangwa se virtual image. Ikindi, object distance zo nta gihora ari positive. Ikindi ndakeka ari ibyo ngibyo. Focal length yo nayo ihora ari positive. Ikindi, magnification kuri iyo image icuramye, magnification iba negative. Kandi magnification image icurama ryari cyangwa se reba hasi ryari igihe dufite real image. Ari nayo mpamvu magnification kuri real image ihora ari negative. Ibi ngibi buri gihe tujye tubyitaho rwose. Reka dukomeze ku kibazo cya gatandatu. A concave lens of focal length which is equal to negative 20 cm forms a virtual erect half the size of object. Find the object image distances. It's just to use the data we have by using magnification equation and the lens equation. You can find the object distance, even the image distance. You see, because it is the lens is diverging or concave, image distance is negative, object distance is positive. So, question number 7. An object is placed at the focus of a convex lens. Describe the image formed. An object is placed at focus. Object at focus of a convex lens. Describe the image formed. Always, when the image is positioned, is located at focus. At focus, always, when object is at focus, always image also should be formed at infinity. The reason why also the object located at infinity, the image also should be located at focal point. We must know this one. The image is formed at infinity, real, inverted, and highly magnified. An object is placed between the optical center and focus of convex lens. Describe the image formed. When the image is formed at between the optical center and the convex lens, here also we will have a virtual image which is magnified. Means it will be in the same side as object. Let's jump to the ninth question, which is about lens combination. A convex lens of focal length 20 cm is placed in contact with a concave lens of focal length of negative 10 cm. Find the focal length of the combination. Just as we said by the first point, the power you have focal length of the two lenses, the formula, the power of combined the power of combining two lenses is equals to the power of the first lens plus the power of the second lens, then the focal length will be negative 20 centimeter. The focal length of the combination is negative 20 centimeter, which is similar to that of concave or diverging lenses. Two thin convex lenses of focal lengths 15 centimeters and 20 centimeter are placed in contact as an object is placed 30 centimeter from the combination. Find the position and the nature of final image. You have two focal lengths, even the object distance. Here there is this negative is not necessary. It's just a very short case. You will correct it, but the necessary the way to do this one is just when you have the two focal lengths, we will be able to find the power of the power. The reason why I am saying power, the power of a lens equals the inverse of focal length. When you say 1 over f means is the power, the total power. 1 over f1, it is the power of lens 1. 1 over f2, it is the power of lens 2. So that the focal length of combining the lenses equals to 60 over 7 centimeters. After getting this focal length, I will use the lens equation to find the image distance. So here also I have unsolved the questions. I will try to read them quickly because time is moving. There is basic calculations. I think we have 20 questions, which are in 3 cases. Question 1, part 1, question number. The first part is about basic questions. These basic questions will help us to find the relevant information for basics about these lenses. The other question about question number 5, it is image formation and the characteristic. 9 and 10, lens combination, power of lens. 11 and 12, lens maker formula from 14, and practical applications. We can try these questions ourselves because it's a very simple to get and to see. Let me hide this because I'm not able to see this image. So now for this unsolved questions, basic questions. Question number 1. A convex lens has a focal length of 20 cm. An object is placed 30 cm from the lens. Find the image distance and magnification. A concave lens has focal length of negative 15 cm. An object is placed 20 cm from the lens. Find the image distance and magnification. We will try to read them quickly. So, an object is placed 25 cm from a convex lens and forms a real image twice the size of the object. Find the focal length of the lens. A 5 cm tall object is placed 40 cm from a concave lens. The image formed is 3 cm tall. Find the focal length of the lens. 5. A convex lens of focal length is 15 cm forms a real image. Invert the image 3 times the size of the object. Find the object and image distances. A concave lens of focal length negative 20 cm forms a virtual erect image half size of the object. Find the object and image distances. An object is placed at focus of a convex lens. Describe the image formed. Question 8. An object is placed between the optical center and the focus of convex lens. Describe the image formed. Question 9. A convex lens of focal length 20 cm is placed in contact with a concave lens of focal length equals to negative 10 cm. Find the focal length of the combination. Question 10. Two thin convex lenses of a focal length 10 centimeter and 20 centimeters are placed in contact. An object is placed at 10 centimeter from the combination. Find the position and the nature of the final image. About power of lens. A lens has a power of positive 2 diopters. Find its focal length. A lens has a focal length of negative 25 centimeters. Find its power. 13. Two lenses of powers positive 3 diopters and negative 2 diopters are placed in contact. Find the power of the combination. About lens maker's formula. 14. A double convex lens is made of glass with refractive index of 1.5. The radius of curvature of the two surfaces are 20 cm and 30 cm respectively. Find the focal length of the lens. Question 15. A plano-convex has a focal length of 20 cm. The refractive index of the glass is 1.6. Find the radius of curvature of the curved surface. Let's look about practical applications. Question 16. A magnifying glass has a focal length of 10 cm. At what distance should an object be placed from the lens to produce a magnified image 3 times the size of the object? Question 17. A camera lens has a focal length of 15 millimeters. If the distance between the lens and the film is 5 millimeters, how far away should the object be placed to form a sharp image on the films? Question 18. A projector has a focal length of 30 centimeters. The slide is placed 32 centimeters from the lens. Find the distance of the screen from the lens and the magnification. Question 19. A person is nearsighted with far point of 15 centimeters. What type of lens is required to correct this version defect? Find the focal length of the lens needed. Question 20, which is the last question. A person is farsighted with a near point of 50 centimeters. What type of lens is required to correct this version defect? Find the focal length of the lens needed for reading at a distance of 25 centimeters. So thank you so much. This is about for today's session. Let's try to collect individually, even as a team, according to where we are located. So next time we will try to answer the question individually or by this platform. Note, this question covers a range of difficulty levels from basic calculation to more complex concept. You can adjust the difficulty and specific topic based on your students' knowledge and depth of coverage required. I hope this is quite very simple. So thank you so much. Let's meet next time. God bless you. Let's meet the next time and session. And remember to subscribe to this channel, give us comment in order to share more and more questions related to this point. Thank you so much. God bless you. We will meet next time. Thank you so much. God bless you all.